Hello, welcome to the Lab 5 help session. I'm going to go over Moore and mealy outputs and then an ASM diagram, and then Landon will cover VHDL. Alright, so a couple ways to describe Moore and mealy are that Moore depends solely on the state, and then the output would always be true for that state, and mealy depends both on the state and the input. So what that looks like is, for Moore, you would have an output called red, and that is within this state box. So this is state 0, and this is the output red. So no matter what, for state 0, red will always be true. Now for mealy, you wouldn't put it inside the state box. You would put it outside the state box in the ovals. So for mealy, nothing is true for the entire state. However, when you go to input X, when it's true, yellow will be true, and when it's false, orange will be true. So putting them together, you can have a Moore and mealy outputs. So for this state, state 2, green will always be true, and then when input Y is true, green and purple will be true, and when input Y is false, green and blue will be true. So the goal of the ASM is to describe each of the states, the inputs, outputs, and the logical progression. Alright, so I made up this ASM example with an elevator. Imagine that we have an elevator going between two floors. It moves up and down just automatically. When the doors close, it moves to the state it's not on. Or sorry, the floor it's not on. And then the input is the door open button, and the outputs are open, closing, closed, moving, floor 1 and floor 2. I could have combined open and closed so that when one is true, the other is not, but I wanted to make it more clear what's going on. So for the states, we can either be on a floor and display what floor we're on, or we could be moving. So starting with state 0, we're on floor 1, which is outputted here. Imagine you have an LED or maybe a hex to 7 segment display, and you start with floor 1. And then we also have open, so the doors are open in this state no matter what. Then we move to the next state, in which, again, we're still on floor 1, but then this state depends on the input of door open button. So when it's false, it's closing, as you would expect. But if at any point before the doors fully close, door open button gets pushed or becomes true, it then opens the doors again and goes back to this state and waits some more. The time that it waits would be whatever you program it to. All right, and so when it's false and it does complete its closing, it then moves to the second state, in which it is moving. And when it's moving, the doors are always closed and they're never open. Because imagine when you're in an elevator, the doors will always be closed when it's moving. All right, and then so this A circle right here is just linking it to this A circle here. So it's moving from state 2 to state 3, and we have the same logic from here over here. So we're on floor 2 and the door is open, and then we move to this state. So we are on floor 2, but the doors are either open or closing depending on the door open button. All right, and then we move down here to, again, moving and closed, and then it goes back to floor 1. All right, thank you for watching. Landon will take over with VHDL now.
All right, thank you. So now we're going to go ahead and jump into VHDL. We're going to talk about some syntax, and then we're going to go ahead and implement Joseph's elevator ASM. So to first start off, VHDL, the name is a little misleading. So the V stands for Very High Speed Integrated Circuit, and then the HDL is Hardware Description Language. So the two main blocks of VHDL is going to be the entity and the architecture. So the entity is, you can think of it as the black box, the inputs and the outputs, and the architecture is the entity behavior or the logic that lies within. So if you look off to the right, this is kind of a good way to visualize it, where the entity will encompass things in and out of the system, and the architecture will describe how those inputs will interact with each other to create our necessary outputs. So then this is actually where the name top level entity comes in that you've probably seen in your past labs. So when you think about digital design, what you do is you create a collection of sub-entities nested under a top-level entity, and that way you can put together a full design in small pieces. So if you look off to the left, you can see we have our top-level entity here in blue, and each of these green boxes will be considered our sub-level entities. So for example, this one might be an adder. This one might be an encoder. They both combine to go through a combinational logic block and then a decoder. So here's a very simple design, and you can see how the top level entity is basically what will connect all of these different sub-level entities. And then each sub-level entity will take different inputs from the overall entity. So this is the importance of creating your block diagrams when you make a design, because if you're in industry, maybe the design you make will go and be a bigger part of another design. So for this lab specifically, what you're going to be able to do is write your VHDL and then generate that block diagram afterwards. So if you are on the website and under this lab 5, you can see there's a link creating graphical components. So please review this document for creating a block with your VHDL code. You will then use this block and put it in your block diagram file or PDF, and then all sequential logic will be done with flip-flops like normally. So in terms of VHDL syntax, it's a little different than some of the other languages. So for one, it is case sensitive. So a capital C and a lowercase c are two different variables if you're defining something like that. Similar to languages like C++, we have a semicolon used as a terminator. So this basically is like the period in a sentence. For comments, we basically have two of these, I guess, hyphens. So you'll see a comment start, you'll do two of the slashes, and then the text will turn green, and that's how you know a comment has started. So for comments, that means it will not get interpreted when in your code, and it's only for readability purposes. So parentheses is very important in VHDL as it helps organize your logic. So VHDL doesn't follow like PEMDAS, where it'll do multiplication first or like and first. Basically, it's just generated from left to right, which is why you need parentheses, just how you would need it in math. And then this less than equal sign is your assignment operator, which we'll see in a little bit later. It basically, when you have your signals, you have all your logic and you store it to your signals. You can kind of think of it like that. So let's go ahead and hop into this Quartus demo. So if you need a quick refresher, this is the ASM Joseph covered earlier in the video. You have basically an elevator, floor 1. The door open button is your input, and then you have two mealy outputs, one for open, one for closing. And you can see off to the side, I took a minute to kind of do the truth table. So you can see these Qs are going to be our current state. So here in 0, 0, 0 would be right here. And when you're in this state, it doesn't matter what the input for door open button is, since that only exists in 0, 1. So for here, you can say I put a wildcard, which encompasses both the true and false for door open button. And you can see after 0, it'll go to state 1. So I'll leave this here for reference, and we might reference it while writing our code. But yeah, we'll go ahead and move into Quartus and see how this will kind of look. So moving into Quartus, what I want to do is create a new VHDL file. So similarly to a block diagram file, I'll just hit this blank paper and we'll go VHDL file. All right, so now you can see we have a blank page. So what we want to do is kind of do the skeleton, and this will be constant for any VHDL file. So first, we want to do library IEEE, and then use IEEE.std logic _1164.all. So this is basically doing a library, just like anything you would do in Python. And this allows us to use certain keywords to write our code. So like I said, any VHDL code has an entity and an architecture. So we'll start by writing our entity. So we'll say entity, and then here we'll just say live video is port. And then this is where you'll have your ports right here. So basically, this is the name of your entity. And what we're going to do is we're going to save this file as live video. So it's very important. This entity name is the same as the name of your file, or it'll throw some weird errors. So keep this in mind when writing your code. So in this entity, we're going to put our inputs and outputs, but we'll go ahead and write the behavior. So it's architecture, behavior of live video is, and then we'll go ahead and write begin, and then at the end, we'll say end behavior. All right, so this is the basic structure for how our code will be structured. So in terms of our actual understanding, for this example, let's go back to the PowerPoint. And you can see for inputs, we need these 3 state bits and this door open button. So those will be our 4 inputs. So we'll nest that under our entity. We'll say these are the inputs. And we'll do our first input, which is door open button. And since it's an input, we have a colon and we'll say in std logic and then close with a semicolon. So we're going to do this with the 3 other state bits. So Q2, Q1, and Q0. So now these are going to be our inputs. So another thing that I personally like to do is just I'll tab these over so they're all in a line, and that helps the readability of your code. So now for our outputs, we'll go ahead and let's see, we'll need to do our next state, or this will basically be going into our D flip-flops. We have floor 1, floor 2, moving, door open, door closing, door closed. So we'll call our Ds. This will be going into the flip-flops. D and then outs is another keyword because we're doing outputs. And we'll need to do this. So these are going to be D1 and D0. And then we'll also need to do F1 and F2, indicating which floor we're on. And then we're going to do basically the state of our elevator. There's going to be 4 here, where this one's moving, door open, door closing, and door closed. So then I'll go ahead and line these up. Nice. So now we have very clean inputs and outputs. And then one more thing that I noticed here since I was copying and pasting that will actually throw an error when we compile is right here. Do you see how they all end with a semicolon? So your last output doesn't actually need a semicolon. A little weird quirk of VHDL because you can consider this semicolon taking care of that. All right, and then I guess for our entity, another thing we need to say after this of ports, we'll say end live video. All right, and then we'll add some semicolons here as well. So this is our entity, and now for behavior, since you can see it's a pretty long truth table, I'm only gonna do, let's say like the first line for D2. So what I find helpful is when you write these codes, our inputs are reliant on 4 inputs, Q2, Q1, Q0, and DOB. So I always like to have a comment right here, and this will help you in the long term, is we're gonna have this whole section and we're gonna do OR, because this is basically what we're gonna do is write a sum of products, and VHDL will do all the simplification. So you can think, and then we'll do basically the combination of all of our outputs, and then we'll do that knotted. And you'll see why that is in a minute. So we'll say not Q1 and not, I'm sorry, let's do this in the right order. Q2, Q1, and not Q0. And then finally, we'll say and not DOB. All right, so you can see this is basically saying like 0, 0, 0, 0. So then when we write our code, we can actually copy and paste this line and it'll make it easier. So let's go back. So if we do like D2, you can see this will be true under 3 conditions. And although it's 2 rows, you've got to remember this wildcard will be 2 rows, I guess, implicitly. So it's 0, 1, 1, 0, 0, 1, 1, 1, and 1, 0, 0, 0. So another way is, since this is a wildcard, you could just consider these 3, but for the sake of this code and for this demo, I'm just going to go ahead and include all 3. So here, we're going to first do 0, 1, 1, 0. So now that we have this kind of template, it'll be very quick. We'll say D2 in our assignment operator, and we'll have this. So remember, we're doing, for D2, it's 0, 1, 1, 0. So this is 0, and then here, we're going to do 3 spaces. Here, 3 spaces as well, and 0. So that's our first line. And the next one, considering the wildcard, will be 0, 1, 1, 1. So we'll go here, paste another. We can copy and paste these 3 spaces. We'll just replace the not. Nice. So now we have, and then finally, we'll do this one right here, 1, 0, 0, 0. So we'll copy this. And this will be 1, 1, 0, 0, 0. And then we'll end that statement. So you can already see right now why I made this template and why you replace a not with zeros. Because now this makes debugging your code 1,000 times easier rather than writing them all in a line. You can go step by step and see this is 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0. So this is the basic structure. And now we're going to go ahead and see how we're going to make a block. So I went ahead and wrote the VHDL code ahead of time just to save us some time. So you can see we have our inputs and outputs that we've already defined with some comments saying DOB is door open button. Yeah, so end of our entity. And this is all of the architecture. You can see I have the same template right here. And all of our code is in a line and it's very readable. D2, D1, D0, F1, F0, moving, door open, door close. And then we're ending behavior. So now that we have this code, this will handle all of our logic for now rather than putting them through gates. So now we want to be able to put inputs and outputs into our system. So what we'll do is we'll go up here to File, create an update, and create symbol files for current file. And then we'll just delete this for now since we already have what we need. So then after you create this file, you can go into a BDF, like this one, for example. And if you go here to symbols, or yeah, symbols, and you go here to projects, you can see that our symbol is right here in the order that we made them. So yeah, we already have the block in here. So you can see this is basically putting our inputs and our outputs into our system, and we can use that to actually do our design. So you can see here I have the D flip-flop, so the D2, D1, and D0 will come out. You have our asynchronous start lows. These should really be tied to VCC since they shouldn't be left hanging. And then inputs and outputs right here. So now we can actually go and run our simulation and see if this makes sense. So I went ahead and did it beforehand. So we'll go ahead and click run. And then we will compare this to our ASM to make sure it makes sense. So one thing that's very important in this class is creating good simulations. So we learned in the past labs, it's not good just to run through all the combination, and it should make logical sense working through these. So let's see, we're gonna try, let's split screen this one and then our ASM here. Yes, I also have it. Yeah, here we'll do this. So let's go ahead and just zoom into this first section and take a look. So you can see when start active low goes low, all the states reset to 0. And here I have our current state, our next state, and then all of these door closed, door open. So in state 0, which is right here, you can see our next state is 0, 0, 1, which is what we expect. Since whenever you're in state 0, floor 1 and open will be true, we can see that reflected here, door open, and floor 1 is true. And then on this next clock edge, you can see this next state is now our current state, and we're in so 0, 0, 1. And now you can see for the first half of this state, I have door open button being false. So when it's false, we have closing being true, door closing right here, and the next state being 0, 1, 0. But now you can see in the middle of this state, I actually make door open button true. And you can see this automatically switches our next state from going to 0, 1, 0 up to going to 0, 0, 0. And now you can see our inputs or our outputs change. So the door is no longer closing, and now door open is true right here. So that's why asynchronous mealy output, mealy is immediately. So right when this input changes, our mealy output changes. So you can see this will kind of go on. As long as door open button stays true, it'll basically cycle through this loop at the top, going from 0 to 1 to 1 to 0 to 0 to 1. And then eventually DOB goes false. And on this next clock edge, we'll continue. So now we're in 1, then we go to 2, then we go to 3. And feel free to pause the video anytime and just check. Scrolling through, it should make intuitive sense. So now when we're in this state 1, 0, 0, I make door open button true again. And now we loop from 1, 0, 0 to 0, 1, 1 to 1, 0, 0, which is in this loop right here. So that's pretty much it for the Quartus demo. I tried to be as quick and concise as possible by still giving you all the information. So just to wrap this video up, this is going to be our pre-lab procedure. We're going to design a state machine that will control a traffic light according to strict timing specifications. And you'll demo this functioning on your D10 light. As always, every lab needs a video demo, so please make sure to turn that in. All right, that's going to be it for this video. Thank you for watching. Good luck on your labs.